Thank you. Thank you for a very nice introduction. And it's a great pleasure to be here. And thank you very much for having me and giving me this chance to talk about my research. So today, this is the question I have I want to answer from the throughout this talk. So the question is how to regulate star formation process to explain the rate we observe or sometimes we need. So this is a question about how fast do the gas convert to stars. And it's also the question about how fast do we really return the energy from the star to the gas reservoir. So this is a kind of interesting question. One reason is because this actually quite different from what we can really naively expect from simple expectation. The star formation rate, we can write star formation rate as this kind of simple equation with the available total gas mass divided by some time scale. And this star formation time scale may be free fall time or the gravitational time scale when there is no kind of some significant support from the other terms like pressures, thermal pressure or turbulence pressure, etc. And also one thing we know is the gas is highly dissipative and it cools so rapidly. So within some time scale, especially about some free fall time or dynamical time scale, gas is expected to lose their turbulence energy and also expected to cool down to very low temperature. So some naive expectation, we can just write down the star formation rate simply with the gas free fall time. But that's not really true when we really look at the all the star forming system from very small scales to the large scale. So this is an observational result for the individual star forming cores. We can, in this plot, the y-axis is kind of measure the star formation rate. Especially they kind of counting young stellar object to measure this star formation rate. And then the x-axis is the gas surface density divided by this gas free fall time, which is somehow naive expectation of the star formation rate. And then you can see, maybe it's hard to see, but 2 by 2 is there. So that's about 2 orders of magnitude difference between this somehow real measured star formation rate to the naive expectation. So we can, this actually implies that only kind of 1% of gas has been converted to the star during this free fall time. So that is different from what we simply naively expect. Another plot for this low efficiency is coming from this galactic observation. So all dots here representing the entire galaxy itself. So it's on average over the entire galaxy. And then the y-axis is again the star formation rate that is measured from the using the UV IR radiation. Maybe in this case I think it's H alpha. And the x-axis is the another expected simple estimation for the star formation rate using the orbital dynamical time scale. Then we again get about 2% of efficiency per this dynamical time for this entire galaxy. And lastly, in very large scale, we also see such kind of some low efficiency of the star formation rate, star forming efficiency for entire structure within the galaxy. So what this shows is this stellar mass function. And the red dashed line is the stellar mass function inferred naively from the dark matter halo mass multiplied by the cosmic baryonic fraction. And this blue line is a kind of stellar mass function inferred from some observational result. So that shows it has some maximum efficiency at around this, I think this is a stellar mass function. Stellar mass function at stellar mass at about 10 to the 11 solar mass, but at most it's about 1/3. So during the entire history of the universe, gas has been converted to stars. Only 1/3 of them is converted to the star, and it is even more inefficient at low mass halo and also very high mass halo. So this actually leads some speculation for many people to what kind of this leads some speculation for different feedback process that can really lead this kind of inefficiency for gas star formation at different scales. So from this kind of thing, I can just draw some broad, schematic pictures here. So as we form some large-scale structure through the gravitational interaction between dark matters, gas will also fall into this dark matter halo, and then the gas will accrete to the dark matter halo to form galaxies in there. And first, when they accrete to the dark matter halo, it will suffer accretion shock or some Billiard shock that will make this gas to hot state. And then it will eventually fall into the galaxies and cool down. So we have this warm and cold interstellar medium in there, and they will further cool down to the molecular interstellar medium. And all these gas flows eventually go into stars or go into some supermassive black hole. Then the thing we anticipate from stars and the supermassive black hole is some feedback process. So from the stars, especially for these massive stars, they will produce lots of copious UV radiation, which will give us a radiation pressure and high energy photon that can ionize the gas and heat the gas. And also there are a strong wind blown out from this massive star. But among those kind of things, the supernova explosion is one of the most energetic process that we can expect from this star formation feedback. And then they will affect the surrounding molecular cloud and the diffuse interstellar medium, kind of main gas reservoir, and also maybe up to the large-scale hot gas to the intracluster medium or circumgalactic medium. Also, the supermassive black hole can affect all this medium, but for me, it's more uncertain process. I don't really know how they really affect all these large-scale structures from this small, very small accretion disk. So my interest actually just mainly focus on this part of the process, and I will mainly cover somehow to the larger scale feedback to the larger scale, so the effect of the star formation feedback to the larger scale mainly tomorrow. But today, I'm only want to talk about this cycle of star formation and the feedback within this galactic scale interstellar medium. And I mainly want to talk about the effect of this supernova feedback. So, as I said, in this kind of topic, one thing we really want to explain is those inefficiency in gas consumption. But also, there are several observed correlation we may also want to explain. So, some recent observational survey of nearby galaxies that can reveal some spatially resolved information that can drive some star formation rate as function with some different properties. So here you see some example of CO observation that can give us a molecular gas information. And this is H1 observation that can give you us an atomic gas information. And this rotation curve will eventually give us some mass budget of the galaxy. And the old star, they will give us some stellar potential or stellar mass information. And from last column, this will give us a star formation rate that is derived from some composition of the UV and mid-IR and H-alpha observation. And then they actually kind of analyze this somehow pixel by pixel for the given pixel of this about 750 parsec resolution. So that what they got from this recent survey is a colored contour here. What this shows is a star formation rate as a function of the total gas mass. And there are lots of other points that overplotted here, especially including this original Kennicott observation that for the entire gas average. And so this is a kind of one famous relation we actually use, the astronomers really appreciate about, which is called the Kennicott-Smith relation. That is a relation between the star formation rate surface density and the gas surface density with this single power law over this wide range of the wide dynamic range. But now, actually, this single power law relation seems not it's not working, especially for this low gas surface density region. When we go to some like a gas surface density at around 10 solar mass, this correlation turns to somehow steeper slope, and it will give some about 2 orders of magnitude different values for given gas surface density. So the scatter gets increased. So this current modern view of this Kennicott-Smith relation tells us that there are some different parameters that is more important than gas surface density or gas total budget of the gas mass. There will be something we are missing in just simple naive relation. And also another thing we may want to look at is this kind of region where we kind of see some almost linear relation between the surface density, star formation rate and the gas surface density, which is actually got more interest from other observers. And then turns out to be there is some well-defined linear correlation between star formation rate surface density and the molecular gas surface density. But it still showed this gas depletion time from this molecular surface density and the star formation rate relation. We can get this very long gas depletion time, about 2 giga-year, while their usual preferred time is about 10 million year level. So it also still tells us about very inefficient gas consumption. So, and that may also tell us that some people may want to argue that this molecular gas is kind of a cause or somehow necessary condition to form stars, but it's maybe just effect. When we collect all the gas into some denser region, they just form the molecular gas before form stars. So that gives us some nice correlation, but it doesn't really tell us about any kind of physics in there. So there is still this kind of correlation, but we should interpret this as with some caution. And another thing is actually when we look at this star formation rate as a function of also including some factor with the stellar surface density, or we can just plot here's not just, this is not the star formation rate, this is a molecular fraction as a function of this middle plane pressure. So there is some good correlation, and since we know there's some good correlation between the molecular gas and the star formation rate, this may also tells us there is certain correlation between star formation rate and the pressure. So there are a bunch of correlation that we observed. So in this kind of topic for the galactic star formation rate study, what I want to really explain is how can we explain this inefficiency in gas consumption. And also, we also want to give some physical interpretation for all these empirical correlations. To do that, I want to really understand this star formation process from this galactic scale interstellar medium. But it turns out it's very difficult because these stars are born in very turbulent and magnetized and multi-phase interstellar medium. It's not just simple collapse. So this is very difficult. And there are lots of feedback processes we may want to consider from these stars that mediate all this turbulence and the thermal pressure to the interstellar medium. So this subject is actually a kind of star formation that including all these different pressure support term, mainly mediated by this star formation feedback. I'm not really want to argue in details, but at least this scales about like a kiloparsec scale of galactic disk, and for the diffuse interstellar medium where the gas is mostly in the atomic phase, the radiation and cosmic ray pressure is not that important in regulating star formation. The main thing is this turbulent and the thermal and the magnetic pressure, and we should include this self-consistently with this star formation. So let me give some simple theoretical model for this self-regulation of the star formation first. In this model, I just want to focus some local region. It's kind of the one single resolved element of that some nearby survey observation. And we can just look at this kind of disk, local disk region. And the star formation made triggered when this kind of disk is say compressed or the gravity was dominated. Or star formation is actually quenched when this disk was popped up or by the pressure was dominated. So this is kind of simple one-dimensional feature we can actually think, and then eventually if the star formation feedback is efficient enough, that's kind of our assumption, and it will be proved by our numerical simulation, they will reach some equilibrium state, which is called so-called hydrostatic equilibrium, but it's not really static, so I prefer to call this as a vertical dynamical equilibrium. So when you just write down some simple momentum equation and just taking the horizontal average, and you will always have this vertical component only. And then just taking the vertical integration to this equation, and this right-hand side, what you got is the weight of the gas under some certain gravity. So this is when the self-gravity is dominated, and this is when stellar gravity or dark matter gravity dominated. And in left-hand side, what you got is pressure support term, and since this is representing some difference between the middle plane and some vertical height, where if we take this Gmax somehow larger than gas scale height, actually this gives us the middle plane pressure term. So that here you can see there is a contribution from thermal pressure and the contribution from the turbulence, and there is some contribution from the magnetic pressure, and also this is a negative term from the magnetic tension. So this is kind of some hydrostatic equilibrium statement, and we can just assume, we will assume that that will be always satisfied if the feedback is efficient enough to provide this kind of pressure terms. So then we want to figure out how those feedback, how those pressure terms are kind of provided by star formation feedback. So first, let me talk a little bit about some details about the thermal pressure. And in this interstellar medium, we have lots of different cooling, different coolant ranging from some fine structural line of this carbon and oxygen, and also recombination line emission that can cool the gas. And there is a heating from the cosine ray heating or the X-ray heating and the photoelectric heating. And then we can see that it's mainly dominated by this C plus cooling and the O, so neutral oxygen cooling. And the heating is mainly dominated by this photoelectric heating. And this photoelectric heating is actually a photoelectric effect on grains, and that is comes the photoelectric effect from this phi UV radiation. And if we just take all this, consider all this balance between this heating and the cooling, we will get this thermal equilibrium curve. Here what you see is the density and the pressure, and this line shows the thermal equilibrium state of the interstellar medium. Okay, and then the one interesting thing here is actually when you go in this kind of equilibrium state, you will always suffer so-called thermal instability. So for some isobaric perturbation, if you move this equilibrium state to here, below this curve, actually the heating is dominated, so that will keep heating your gas to this range, and if you just perturb this thing to the cooling dominated region, it will keep cooling, and then it will drive to this kind of state. So there are this equilibrium curve actually can range from temperature from about 10 Kelvin to the 10,000 Kelvin, but with this range of the temperature is not really allowed due to this thermal instability. So we expect there is only warm or cold medium in the interstellar medium. But it's maybe not true when this, the dynamical process come into play. But actually, this cooling time is usually very short, though. So this thermal instability working quite rapidly. So they usually saturate with this kind of different kind of two-phase, so-called two-phase structure of the interstellar medium. And in this picture, actually, the interesting thing is the cooling doesn't really change much, but the heating can change as you change the phi UV radiation field. So if you go to stronger phi radiation, the heating goes high, and then the thermal equilibrium curve go up. And if you have lower phi UV radiation, then this heating goes down and the thermal equilibrium curve goes down. This gives us quite interesting result. So let's say we have this two-phase structure, two-phase interstellar medium with some certain pressure that may rise around this way, this region. But for some reason, if you just increase the heating rate, or if you just promote some star formation. Somehow that gives heating the 5 radiation larger than what you usually expect from this equilibrium state. Then this this equilibrium curve actually goes up. And this warm medium can still be in the thermal equilibrium. But now this cold medium actually is here where they fall into the heating dominated region. And then they will actually evaporate to the warm medium. Then you will lose some certain amount of a cold medium. Then that actually suppress your star formation, and it will decrease your heating rate again to some equilibrium state. And the opposite is also true. So that they always, when we have some certain equilibrium, so in this kind of some self-regulation process, due to this kind of self-regulation process, we always expect some certain pressure that will fall within this 2 pressure range, and that will form a cold and neutral, warm neutral medium, even if there is no kind of additional source of the radiation or source of the compression or other kind of thing. So when this kind of heating rate is dominated by somehow local this interstellar radiation field coming from massive young stars, then this will always true that the thermal pressure should go with this star formation rate substance. And another thing is, it's actually a bit, another thing is actually this turbulent pressure. So without turbulence driving, we know that this turbulence will dissipate in flow crossing time. That is usually about 10 million years for this typical range of the parameter. And then, so this is actually much longer, much shorter than what we really observe for this gas depletion time. So that there should be some energy replenishment from this star formation. And also this turbulence, we also always observe this kind of high level of turbulence. So this kind of turbulence is mainly driven by some momentum injection from massive young stars. And among them, the supernova feedback provides the largest momentum per mass of the new star formed. So this is parameterized like this way. This P star is total momentum per kind of event of the feedback. And this M star is the mass of new stars per this kind of event. So this is about 100 solar mass per given IMF. And then we measure these P stars per supernova remnant evolution, and that will always give this range of the momentum injection. And for other kind of source of the momentum, like wind and the radiation, it's usually about an order of magnitude lower than this value. So we want to say that the supernova feedback is really mainly is dominant source of the momentum injection, especially for this diffuse interstellar medium. Then what we can say is this, since this will be dissipated, so there should be, if turbulence has been disappeared, then this star formation will occur within this free-fall time scale, which is much shorter time. So that then will form stars and then will feed back the momentum and will drive turbulence again. So this should reach some equilibrium state that where the turbulence dissipation time scale, dissipation rate is comparable to the driving rate. This driving rate is actually proportional to the star formation rate. So from these schematic pictures, we can write down some diagram that can show this energy momentum equilibrium where the when you lose your energy from the ISM, star formation will give back those energy to the interstellar medium that we want to maintain all this support. And from this vertical dynamical equilibrium, we always need a certain level of the pressure support to support this weight of the interstellar medium. If it was lower than those requirements, it will compress and promote star formation and will increase pressure again to reach this equilibrium. So all this kind of process will reach some equilibrium just when those feedback process is efficient enough. And in terms of the equation, we can see like this way. And then finally, since if we can replace these terms with these two, sum of these two, that will give us a star formation rate should proportional to this one. So that gives us some certain correlation between the star formation rate surface density and also gas surface density or some stellar surface density. It can be some combination of them. Sometimes it can be just gas surface density. So all these things will naturally comes from this equilibrium model. So it sounds quite promising. So there are lots of assumptions we actually made. So we need to confirm those kind of assumptions. So basically what we did is we did direct numerical simulation to check this validity of the equilibrium. And I said that some certain process of the thermal equilibrium and also turbulence equilibrium, how do they really work together? And what are this feedback yield or feedback efficiency, which is we defined as this pressure divided by the star formation rate surface density, that measures some efficiency of given star formation event to provide this pressure support. So we can measure this for total term or for each component. Actually, I didn't really include the effect of the magnetic field here right now, since I expect that it will take a bit more time. But if you're really curious about that, let me just ask me later. I can tell you a little bit more about this magnetic field thing. That's quite interesting, actually. So the simulation setup this is kind of some simulation we did. So we considered just local patch of the galactic disk and running this kind of simulation using this so-called local shearing box that is rotating with galactic rotational velocity and including their difference as a function of radius that give us a shear. But we didn't really include the curvature term of this global curvature term of this disk geometry. So we use this local shearing box information, and then we run some different for different parameters of the gas surface density and the stellar. So this actually measures the strength of the vertical gravity from the stars. So each point actually just each of simulations, and then this is kind of some condition that represents the solar navel condition, and we changed other parameters to check other properties like heating efficiency and the magnetization. But so I mainly focus on the main results that about this turbulence and the thermal pressure, but all this other variation I can also talk with you later. So this local shearing box simulation is quite, sometimes it looks quite strange. So since we are considering this galactic differential rotation, your local box actually was periodic at some point, and then it actually sheared out. So inner region will go faster, and outer region will go slower. Then the periodic condition is not actually real periodic. you need to take into account those shear effects. And those boundary conditions actually give some periodicity along this line. So it also changes with the time, and then it will eventually recover some periodic conditions. So this is kind of decent technique to include all those differential rotation effects in this local simulations, and that allows us to go some higher resolution. So there are some limitations, but we want to rely on this method. And then we solve this ideal MHD equation within this Schrödinger box and applying the outflow condition in the vertical direction. And we include gravity and the cooling and heating that I mentioned. And in this simulation, the important thing is kind of important like cheating is this supernova momentum feedback. We just fixed the momentum injection per supernova event, and each supernova event is just considered as some instantaneous explosion. When we form a dense cloud, we don't really follow any stellar evolution, and we don't really follow the real evolution of a supernova remnant. We just, when there is enough high density, and we can infer some small-scale star formation rate, and then we can convert stochastically those cells into the supernovae that will give us this spherical expansion. I will come back to this kind of limitation later, but this is a kind of one a good method to check the proof for this kind of to prove this kind of concept we have mentioned for the theory. And also, we change the heating rate as a function of the star formation rate. So the heating rate changes with time, but it doesn't really change with the spatial. It is spatially constant. So that means we are kind of considering some optically thin rhythm, but it may be not correct for some high density rhythm. But in solar neighborhood condition, we believe it's quite okay. So this is a typical evolution movie that I will show you. So let me first show you this surface density evolution. So, okay, so these red things are high density region, and the blue things are low density region. And since we include this cooling and heating, that will produce cold neutral medium and warm medium. And also we include this gravity, so those cold medium will grow their density, and then it actually, it will form this some distinct denser region that will eventually explode as a supernovae.
So the bulk velocity trend that you see there is because of your local shearing boundary?
Yeah, this is a shear effect. So the inner region goes faster than the center of the simulation domain, and the outer region goes slower than the center of the simulation domain. So you may see some wavelet structure appears, but it is very disrupted by this supernova feedback. And this is a kind of sideways view for the average density. And when there is no supernova feedback, actually there's some. So this is actually a slice of the radial vertical domain, and you will see this kind of some periodic fluctuation when it comes. When it compressed, the star formation is triggered, and then they will pops disk up again, and then it will reduce the star formation rate, and it keeps going this way to maintain the equilibrium state.
What are the typical masses of the little clumps that you're
It's about density of 10 about 1,000. So due to this, let's say this is 2 parsec resolution. So how much it will be? So based on our later simulation from the sync particles, that's about 1,000 to the 100,000 solar mass. Yeah. It ranges from about few thousand to the 100,000.
And so you're adopting some sort of salpeter ion to determine the star.
Yeah, so it's kind of Krupa. Yeah.
I guess you get and the number of supernovae, or is it?
Right. So that gave us about that the M star, which is the mass of new stars per supernovae. Yeah. Mass of new star formed per supernovae. That is about 100 solar mass. So this is a time evolution of star formation rate, surface density, and the midplane turbulent pressure, and the midplane thermal pressure. That is averaged over the horizontal direction, and is a time evolution. So you may see some different trend here, but this is the pace of the where we just drive turbulence by hand. Because without it initially just vertically collapse and then make some velocity star formation that will give us a much larger fluctuation that we don't really want to go. But eventually when we turn off this kind of driving from this time to here, and they will even saturate the level that we expect from this simple theory. So you can see that it is quite well regulated, and the saturation state goes well. And then we can average those time. We also take those additional temporal average to get this pressure and the star formation rate relation. And then this slope will give us this feedback yield, what I mentioned earlier. And this is actually all the simulation from two-dimensional approximation and full three-dimensional simulation and three-dimensional simulation, but with some thinner azimuthal direction thickness, and also including the MHD model. So all the model really falls well within this range of the relation with factor of 2 difference. And this gives us some simple relation for this feedback yield. And this tells us that turbulent, so the feedback from turbulent, the turbulent support from this star formation feedback is about 3 times more efficient than this thermal feedback. And I didn't really include this MHD effect, but those MHD give us this feedback yield about similar to this thermal feedback yield, which will give additional about 20% of support for a given star formation event. That means we expect about 20% lower star formation rate for a given turbulent support. So it proves our concept quite well. So now let's move on to some real situations. So as I mentioned, it's kind of just controlled simulations with many missing steps, especially for this supernova feedback. So we just assume that, so this, in reality, actually, when the cold dense clouds formed, and there is a very, very deep, very, very complex process to form really stars, and then this is actually we cannot really ever possible to follow. But after the star formation, there is some stellar evolution, which we can track with some simple starburst kind of population synthesis model. And then it will give us some supernova rate as a function of its age, and the phi UV radiation as a function of its age. And with this kind of rate, we can infer at some time we will have this supernovae, and this supernovae actually is, undergoes some evolution from some typical expansion of this blast wave that will boost their momentum from somehow ejecta level to the level we actually used for our simulations. So then the final momentum is injected from this supernovae. So, but in this controlled simulation, we didn't really follow everything, so we just form the supernovae from this dense cloud, simply inject final momentum we expect from this evolution. But now, I want to really include things. In addition to that, we will consider this not just star formation, but star cluster formation that will give some clustered supernovae, and then that will produce not just supernova remnant evolution. It will make some superbubble due to this multiple supernovae event, and then the final momentum per supernovae is injected, which may be different, but fortunately, it's a multiple supernovae. You can think this as each supernovae event. It's because this is a kind of simple test simulation toy model, with some constant interval. Sorry. But yeah, this is a quite simple simulation, but we can infer lots of things from here, actually. But yeah, fortunately, we did change the background density and change this time interval with some different parameters. But we always get quite similar range of this momentum injection per supernovae, which is a level of this 10 to the 5 solar mass kilometer per second. That is actually what we used for our controlled simulation. Not that much, but that's quite similar. But there are definitely some difference. So if we really realize, we really use this supernovae individual as explosion with this detailed evolution, that may give us better treatment for this their feedback. So we kind of conduct this project. We called it as Tigris, which stands for the three-phase interstellar medium in galaxies dissolving evolution with the star formation and supernova feedback. So what we want to emphasize here is we now have this interstellar medium with three-phase, which has we have a hot gas that is heated by this supernova shock, and we actually resolve star formation. That means we don't really follow the details of star formation, but we kind of resolve the clump that has high enough pressure that can be considered as really gravitational bound, that's separated from the background state. And we, as I said, the supernovae feedback is really realized with thermal energy injection that can resolve all the energy conserving stage to momentum conserving stage. So for that, we definitely we need to include self-gravity. But actually, it's quite crucial, but not many this type of simulation really include self-gravity. They kind of just injecting supernovae with some imposed feedback rate. But as I said, this is a kind of crucial point of us to self-regulate the star formation rate. And then by considering those population synthesis model, we include this time delay naturally, and also 5V radiation is calculated from those population synthesis model. And yeah, supernova feedback is resolved since we have a high enough resolution, but in some case, when supernovae actually exploded at very high density, that will not really resolve, then we can just put the final momentum to represent our final stage of their evolution. And yeah, supernovae is actually treated with clustered supernovae and also runaways. So this actually representing the specially distributed supernovae motivated by the star clusters. The young stars, massive stars many of massive stars are in binary, and then when one supernovae exploded, the other will actually can escape with some high velocity because of the supernova kick. Then this will form a runaways that we can model this with simple prescription that may affect some details of the distribution of the hot gas, some temporal evolution, but it doesn't really change. I didn't really include that, but it doesn't really change the detail, the final result of the star formation rate itself. And as I mentioned, also this galactic differential rotation is included using this local shearing box treatment. But I want to also emphasize that this is not really well treated in other group simulations, and that they cannot really go for the long-term evolution because they usually just get end up just a very high density clouds. They cannot really disrupt by their treatment of the feedback, and it's mainly because they cannot prohibit this large-scale gravitational instability. And I don't really want to talk about these dynamo details here. And the long-term evolution is quite important because, as you saw, that the initial condition is always need to be artificial, so that will lead some artificial evolution. So we need to really learn it longer than to reach some state where we can really free from those initial conditions. So here's a kind of evolution of new simulations. So you saw those colored dots that represent star clusters that will host lots of supernovae in there. Its typical mass range is around 10 to the 4 solar mass, and it actually forms together at some point, and then it will produce big superbubble, and those will quench the star formation, and it reduce the feedback effect that will again trigger the star formation.
So can I ask the small dots that I saw?
Yeah, that's the runaways that I represent, that I follow to.
So that's why they had a much larger velocity dispersion.
Right, so that will give us a specially distributed supernovae. It doesn't really affect any other kind of thing, but it just the supernovae will explode it quite far from their original star clusters. So this is a slice view, radial vertical slice and the mid-plane slice. And you now kind of clearly see this is a number density plot, this is a temperature, and this is thermal pressure. And this is a vertical velocity, and this is a magnetic field strength. So you can see when there is clustered star formation event, they will eventually produce this correlated multiple supernova event, and then it will create a large superbubble that actually blow out lots of gas with very high velocity. And those things will pop disk up and hit the gas to the cold, the warm medium that quenches the star formation itself, and that regulate their star formation rate to a certain level. So this is a star formation rate evolution as a function of time, and all different color actually the average different time being. So we can see within the when we saw this some short average time scale, we see the fluctuation of this star formation rate is actually very large. Sometimes it's more than order of magnitude. And then with that, actually, this 5V radiation is really mainly coming from very young stars. So that follows quite well with this 10 million year being of this star formation rate evolution. And then as those 5V radiation changes, the heating rate changes, as I explained, and those gas distribution follows the thermal equilibrium as they go up, down, up and down, up and down. And yeah, I will talk about this tomorrow. Yeah. Then eventually, I got the star formation rate as a function of this dynamical equilibrium pressure, which is a kind of requirement from the galactic condition, that the weight of the gas. And our Tiger simulation, what I showed you is this one, the solar neighborhood condition. And we also have two different cases with a higher surface density. And now it extends our relation with some larger dynamic range, and they are all agree with each other, which means it's kind of somehow definite condition that since this galactic condition always requires a certain level of the star formation rate from this for a given dynamic equilibrium pressure, so that we always get that star formation rate. And now actually we can really compare this with the observation. Here is some recent paper from Rodrigo Herrera Camus, and he did analyze the star formation rate directly, and he compared directly it with the dynamic equilibrium pressure. So previously, observers usually compare this pressure with the molecular fraction, so it was kind of indirect connection. But now they just directly compare this, and then they found our relation actually explains these observations very well.
Shouldn't the correlation be tighter if you're using the right x-axis?
But as I mentioned, so this kind of thing actually, this star formation rate, there are lots of other effects, like this temporal fluctuation may also be one, and the other can be. So this kind of measurement itself has some uncertainty a lot, especially in this x-axis, because this you need to calculate it based on some information of velocity dispersion, and so it's not shown here, but there are some other parameters in there, which it's quite not really well defined, and then they will give us systematics along this line. Then the other thing is actually this is kind of some just simply expected from the dynamic equilibrium, but interesting thing is we can really kind of predict the real ratio between those pressure support, because if they are really coming from the supernova feedback that we modeled, and also they are coming from this thermal pressure that thermal feedback that we modeled, then it will end up reach this kind of relation. And what we got from the numerical simulation without any tuning, those kind of ratio between the pressures. And that is, this is also there are lots of uncertainty in measuring this one, but at least the first try was quite successful, and they measured this total pressure over this thermal pressure, and that their measurement is quite well agree with our model. So, okay, it looks good. And if I just plot usual Koenig-Smith relation, that also quite well agreed. They also agree quite well. We can see large scatter at some given surface density because there are lots of dots, because we mainly change other parameters for solar neighborhood condition. But you see it can be very low for very strongly magnetized case. It can be high when your gravitational potential or this low SD term is high. So this scatter can be natural consequence of that, and other kind of thing is also in right range. There might be, it may looks a bit different for this high surface case, but there are actually an issue for the measuring those gas surface density for high surface density, especially for this CO to H2 conversion factor, which is kind of whole other topics for this kind of field of study. So let me summarize. So this supernova feedback is actually on-demand process to provide right pressure that matches this weight of the interstellar medium. And so this feedback is very efficient, so that it immediately replenish the energy that we lose. So they kind of forced to be to this gas consumption to be inefficient. And from this fundamental correlation, we can explain the secondary observational correlations. And the details of the interstellar medium physics can really change the internal relative ratios of each component of this pressure support. So that actually that is kind of some thing we can discriminate what kind of feedback we should really consider. So based on our experience, when we only include the supernova feedback, that looks okay for everything. So that kind of somehow say that, okay, maybe the supernova is really the dominant source of this turbulent pressure or the feedback. And now this Tigris simulation provides quite realistic three-phase interstellar medium model with a well self-regulated star formation rate, which is quite consistent with observation. So now we can really look at more about this, including the relation between star formation feedback and the hot gas that can be blown out from the disk. So that I will talk about this tomorrow. Yeah, that's all. Thank you.
If you look at a star-forming galaxy, about 1/3 of the supernovae are type 1a supernovae, which don't have anything to do with the massive stars, we think.
Yeah.
I'm not sure. Maybe with a time delay, 500 million years, something like that. What's your sense of how that may change your results? Because I don't think
so. It's mainly give. So let's say, if those type 1a supernovae is like its rate is always constant as a function of time, irrespective of the star formation rate.
No, it's not. I just told you.
No, I mean, if I say like that, and also, then that's always give some certain minimum level of the turbulence. That will give us some support. That will reduce the requirement we need for this immediate response of the star formation. So that for a given dynamic equilibrium pressure, we may expect a little bit lower star formation rate. So that's a kind of thing we can adjust a little bit from this kind of picture. But that, if those numbers of the type 1a supernovae is not that dominant one, then it is still the type 2 or massive star feedback that can really respond immediately to maintain this pressure equilibrium. So if those type 1a cannot provide entire feedback, entire pressure to support things, then we always need this immediate response from the feedback. And another thing is maybe the type 1a is much more spatially distributed, or their scale height is much bit larger than the type 2 supernovae. That is actually kind of the reason why we somehow include this effect with the runaways. So.
So I understand that you are arguing that the details of the feedback aren't so important because you achieve this equilibrium where if the feedback's less efficient, then you have more star formation and things are self-regulating. But then what is this 1% star formation efficiency number telling us? Like that relation of those? Is your goal to eventually predict that, or?
So actually that is quite interesting. So I mean, so let me go through some equations. So, I mean, what I mean by this self-regulation is this star formation rate give this pressure, and this pressure actually related to this. And because this term is actually now it has this kind of term. When we consider only let's say the turbulence dominated region, the coefficient now is this value, which is very large. That means the supernova feedback is so efficient and so large that provide very large momentum feedback, so that will actually reduce this gas consumption quite efficiently. And that number is actually comes from this one, which is coincidentally with about the 1%. And I think that maybe there is another question considering when we see some small scale, like a molecular cloud thing, there is some theory that that kind of calculate those efficiency based on this logonormal turbulence density distribution function. That also give about 1%. Based on this high mass tail is only about 1%. So, but actually this logonormal distribution is also somehow related to this feedback because this width actually depending on the Mach number of turbulence. And then, so that's maybe another kind of, so that is a kind of another way of thinking this process, but let's say it is kind of indirectly incorporate this feedback process in there. Yeah.
Is this equilibrium that you get not in the timer simulations, but the earlier equilibrium that you got? Can it be described roughly as a Q of order 1?
So I mean that's kind of coincident. I mean it actually drives such kind of state. If I measure the large scale Q, and that it actually give us about value around 1 to 2. Yeah, so I mean the large scale gravitational instability that also should be prohibited by this kind of feedback. If not, we always kind of end up to runaway gravitational collapse. So yeah, so I mean it's what causes what and what's the effect and what is the cause. So since this the vertical oscillation timescale or vertical dynamical timescale is shorter than this large scale, so those swing amplification timescale is about orbit time, which is about 5 times longer than in this case. So that mainly this vertical equilibrium is actually the one dominate this time scale. So yeah, I mean this cannot be true when you go some extreme case like a galactic center, where the dynamical time scale is much shorter, and then those feedback just blow everything out, and then there's some you need to wait time they should be come back, but this dynamical time scale is much shorter than those equilibrium cannot be really maintained. So it's hard to say. I mean, in some sense, if you just average it over much larger scale, then you will still get some rough equilibrium. But yeah, those cycles are a bit different, I think.
Okay. So I think it's important to realize that there are two independent effects. One is the vertical equilibrium. So if you increase the star formation rate, you increase the scale height, and therefore you reduce the density and you have a feedback.
Right.
But the other one is independent of the scale height and would happen even if you had a closed box, namely that when you increase the kinetic energy, you increase the virial number, and that simply prevents star formation because you have too much kinetic energy.
Right.
So these two things are really not the same. Right?
I mean, so when you increase those kinetic energy, which means you drive larger turbulence, then it will actually give you somehow larger velocity dispersion.
Yeah.
So that will pop this up, right? And also it also prevents the kind of radial collapse too. So I mean, I think it's go together. It goes together. Yeah.
I have one more question. Anybody else? So just a quick question. Your Koenig-Schmidt relation. I could draw a line through the points that you actually simulated that matches the low surface density end.
Yeah.
So what's preventing you from getting to the high surface density?
So I mean, as I said, there are lots of debate on this those Koenig-Schmidt law for the high surface density region, especially including this XCO, so CO to H2 conversion factor. So when they get this 1.4, is actually they use this gas mass inferred from the CO observations. But since this XCO factor can change as a function of metallicity, and also So we can actually drive some more sophisticated model. Then you can also get some result that is also can be a function of the gas surface density. That will actually stiffen your relation. Will give a sigma squared. That is actually this one. So, I mean, this is a kind of argument that we want to push.
But you haven't simulated those high surface densities. So
No, we don't. But so that's only in the case of the that only shown kind of the highest surface density here is of 100. Yeah. And this actually just if we just stiffen your relation, so this is a relation for sigma squared about. And actually, it's not really just a sigma squared because we also increase these things too. So, yeah, it's not just a simple relation. But the main argument is that we always need to get some certain level of star formation rate that is given by certain combination of this. And in those high surface density case, this will dominate. Then it will follow the sigma squared. And observationally, that kind of conversion will give you a sigma squared. It is possible, but I think it's still there are lots of debate on that. So.